And go ahead and open up the 2D framing. And once you open that, since I have two sets of problem, one is in English Imperial system and the other one is in SI unit, I'm going to just make sure the first one is in SI unit. So let's go ahead and click on tool right here, and then click on job reference. By the way, if you're new to Autodesk Robot, I got a introductory video and go on my channel. You should go look at it. It really help you out. So anyway, once you click this and come in, click on unit and format, and from here we click on matrix and say yes, and we're good to go, and close this and close that. The next first thing, I always like to work in a framework, so I'm going to come up here, click on axis definition, and then start from 0, 0, click add, and the next one is going to be, I think the beam is 4 meter long. Let me bring it up. Yes, it is 4 meters, so I'm going to type in 4 and add, and I want to make those to A and B there, and then I'm going to go ahead and go to Z, which is the vertical direction, and just put 0, 0, add, and that's good enough. Apply, close, and now I can see here's 0 and here's A. From here I'm going to go ahead and put 4 meter in, which is basically at point B right there. And next thing I'm going to do, I'm going to go ahead and click bar right here, and I'm going to select it's already been selected, W16 by 40, and if you want to change it, you can go ahead and click on this button, and that's a story for another day anyway. You can watch one of my other videos to know about this stuff. So now let's just use 16 by 40. I'm going to bring this out of the way right here, and click right here and click right there. That's it. Close out of that, and there's your beam right there. So when you come down here at the bottom, you can see it says a section shape. Click on that and you can see your beam here. Let's put the support system in it, and in this end is a pin and this end is a roller. So I'm going to come out here at the right corner and click on support, and there's a pin. If you don't have anything here, let me delete all those out. Yes, and click all those out there so we can make a new one. Assume you have nothing here, so I'm going to go ahead and click new, and I'm going to go ahead and do the pin. Pin is, normally we talked about it, is a restriction in the X direction and a vertical direction, horizontal and vertical. In here, horizontal is a X and a vertical is a Z, as you can see the picture down here. And let's call that support 1, or you can call it pin. That's good. So support A in this case, or you can just type in pin so you know that's a pin for future. Click add and close out this. There it is. So let's go ahead and do the second one also, which will be right here. Make a pin, take the X out, so all you have is a Z. It's a vertical direction. Click add. Let's call it support B here, support B, and hit add, close. Okay, I'm gonna go to support A. I'm gonna put it right here, and support B, put it right there, and close out of this, and there's both of my support. And if you click this off, you can see it right there. Next, we're gonna go ahead and put a load on it. Come on to the right, or go up here where it says load. Either way, it's the same way. You could do the same load type right here. Click on load type, and we're going to define what kind of load we're going to put here. First, we're going to hit dead load 1 because that's the weight of the material itself. That's not going to concern us for now. And we're going to hit click again, add. So dead load number 2, that's where we're going to put our force on, which is about 3 kilonewton per meter. All right, close out of here. Now come back in here, the icon below the other one, which is the load definition. Click on that. Let me bring this in the middle so you can see them better. So load definition, hit the bar and hit the uniform distribute load. Make sure, see our load is going down, so that means minus in a Z direction. Come down here, type in -3. That makes it -3 kilonewton per meter right there, and hit add. I'm going to come up here and just click on here, and there's my load. Let's close out of here. The load's still there, and if you want to keep seeing it, come down here at the bottom left corner, click on load symbol right there, and then you can click on a number. It can tell you the number is -3. All right, now everything is done. So now we're going to go ahead and run a calculation. Come up here, see this right there, it says the calculation, click on that. All right, and then you're going to come, let's look at the result. You come up here, click the result, and result diagram for bars, and there it is. So now first what I'm going to do, I'm going to go ahead and let me get rid of this for now. There, I'm going to go ahead and figure out the shear diagram. Or we can find the reaction first too, it's up to you. So right here, we're going to click on reaction, and I want to know what's my reaction in X and Z direction, and I'm going to click normalize, and there's my reaction right there. So I'm going to come back up here and click on parameter, and I'm going to see, I want to label and apply reaction right here, normalize. We did that, and description, make sure this was click right there, apply, there it is. Okay, let's get this out of the way so you can see it. It says 6 kip, and our reaction is about 6 kilonewton, and here's our reaction. It's going to come out to 6 kilonewton. Next we would like to get the shear diagram, and then we want to get the moment diagram. See if we can come up with this. All right, let's go back to the robot right here. And so we got those again from same diagram, result for diagram right here. I'm going to go ahead and check these and click apply, so they're no longer there. Now I'm going to go back in here and click on NTM right there. And then I'm going to go ahead and just click on FZ, which is my shear. I don't have anything in the X direction. If you want to click that, that's fine. There's nothing there. And click on normalize. And there's my shear diagram. You can see it. Let me get rid of the bar first. There it is. Okay, and that looked like the PowerPoint. They look similar to this one. 6 here minus 6 there, and 2 meter in the middle, and there we are, and it's 2 meter right in the middle. Okay, I'm gonna uncheck those again, so I'm gonna go to the moment. So now right here, the same NTM section, click on my moment, and then click normalize. And there's our moment diagram. And if you look at the computer here, they show it like this. But robot, it shows it right here, which is a 6. And all depend on your sign convention. All right, let's go ahead and do the second problem. And we're going to go through the same routine again, just like the first one. Make sure I am in okay. I'm going to go ahead and set my system, and that beam is 3 meter long. So that's going to be 0, add right there. The next one is going to be 3 meter. Enter, and go to Z, just 0, add, apply, close. This time I just have both in 1 and 1, which is all right. I'm going to come back here and click my bar. That's fine. It's going to be from 0 to 3 right here to right here, and close. There it is. I'm going to put the reaction on them, support 1. We talked about this one being A right here. Oh no, that's not it. Wrong. Oops. You can always hit undo right here. It's gone. It's going to be fixed. So I'm not sure if that's a fix. I'm going to go ahead and make a new one and call it fix. Make sure all three of them is, and call it support fixed A. Add, close, right there. Okay, so let's go ahead and put a load on it. And that's going to be like this one here. We're doing this problem. It's a triangle. At one end is 2 kilonewton per meter. And it's a 3 meter long. Gonna go to load type. Make sure you have two dead load. Dead load 1 is for the beam itself, weight of the beam. Dead load 2 is what we are gonna put on it. It could be anything. Okay, let's close here and load definition right here. Click on that one, this corner, or you can go up here, click load and load definition, same thing. So now we're gonna go to a bar, and you can see right here we can't do this one, so we're gonna do this one right here. And you have to go ahead and figure out what you want from what end. You see P1 and P2. So if we look at our problem, P1 is 0 and P2 is going to be minus 2 kilonewton per meter. So I'm going to say minus 2, and that's going to be in Z direction. We good? Click add, and we're going to come up here and click on that. And if we get rid of the bar, we can see it. There's our load, and the beam is right underneath it. And if you hit the number, it can tell you what they are. Minus 2 right there. P0 is 0, and Pn1 it is minus 2. And this is, again, this is a fixed end. So let me get out of here, close that out. And you can still see the weight if you want. Come up here and run your calculation up here. And then we can come up here, click result, and diagram for bars. We can find the reaction, moment, everything if you want. All you have to do, come up here, click on reactions, and you can click FX, FSZ, and MOY, and normalize, and they're right here. And if we go ahead and description, apply, it will tell you F is equal 3 and MOY is equal 6 kilonewton per meter. It's minus 6 here. Remember, our sign is different than what it's in the book a little bit. All right, now next one, I want to see the diagram. So I'm going to go ahead and get rid of that. And so come up here, click on NTM, and let's see the shear diagram. The shear diagram is going to be F is Z force, and we're going to normalize it. And our shear diagram is going to look like, get this out of here. This is our shear diagram. And let's see, normalize it so we can see, go to the parameter and click on label, apply, and shear is going to be from -3 to 0, and just like what we have on our result. And you notice this is a curve. It's not a linear. It's a curved. All right, let's get rid of this. Go back to NIM. Take that out, normalize, and next thing I'm going to go ahead, I'm going to do the moment diagram. So click moment diagram, normalize, and there's your moment. It's a nice parabolic curve, and you can see is if you flip this down to the bottom, it looks like what we have in the picture, again because of the sign convention. Our maximum moment is -6, and it says right there, whoops, -6 right there. All right, let's move on to the next problem. Okay, let's do our last problem, and come up here and change back to imperial. I'm gonna go ahead and change the units back to imperial. Yes, good. And the problem we're gonna do is work on, it's gonna be this beam right here. Let's see if I can make it bigger. I'll go through all that. So we have this timber beam, has an overhang on both sides, and pin right here at A, and I mean roller at A and pin at B, and these are the dimension. So let's go get to work. Let me close this out. There we go. And first thing we want to do is go ahead and set our coordinates, and it's the beam is 0, click add, and the next time is 4 feet, enter, and then 10 feet, enter, and 14 feet, enter. And then in a Z direction we just have 0, enter, and that'll be it. Click apply. Okay, so I'm gonna come up here, go right here, click on bar. I'm going to go here to, instead of simple bar, I'm going to go to a beam, timber beam, and that's good. 4x12 is good. If you don't have that on here, you just click this 3-star right here, and up here should says timber. Then you come down here, use lumber, and then you can go ahead and select whatever you want, and there's a variety of 412 right there. Let's go 410 this time. Okay, add, close, and I have 410 right there. Okay, I'm going to come up here, and just like we have on a diagram, so start off from here, click 1 and stop, click again, and click again one more time. There we go, click one more time. All done. And close. Let's take a look at it, see how it looks. Good enough. And we can go ahead and put the reaction, put the support system in this 2 point. So I'm going to come up here, click on support, and the first one was a roller, so I got roller right here. Second one was a pin right there, and click close, and we can look at it, see this better if you want. If you close this out, there it is. There's your beam, and there your support system. Next, we're going to go ahead and do the load type. Click on load type right here. Now you have to, the dead load number 1, click add. That becomes dead load number 1, and that's for the material load of the timber beam itself. So I'm going to click add one more time. Dead load number 2 is what we are going to add. So close right here, and going to come on to load definition. And the first load, outside load, is going to be a concentrator load. So click on node right here, and it's going to be in a Z direction minus. Remember, in here the unit is in the kips, so in here, but it says 250 pound, so 250 pound is minus 0.25 kips. Click add. It's one going to be right here, the other one is going to be over here. Down the middle we're going to have distributor load, so I'm going to click on bar and click on uniformly distributed load, and the value is 150 pound per foot, but we should use kip per foot, so it's going to be minus 0.15 kip per foot. Click add. Click it right here. Come down this left corner, click on 1, 2, 3, and you can see the dimension. Just double check your number. Looks good. Now close this out. Let's run the calculation. If you don't see it, it's okay. You just come down bottom here, click on that load symbol, and there it is. So come up here and hit calculation. All right, and then done. So we're going to go to result, diagram for bars. Let's get rid of this so I can see it better. There. So now in here, I'm going to see the reaction first. I'm going to go click reaction, and I want both in X and Z direction. Normalize. Oh, let's write here description. Normalize. 700 pound each side. Yeah, that's the right answer. So that's good. So I'm going to uncheck those. and I'm going to go back up here, go to NTM, and from here I want to know what my shear diagram is. So I'm going to click FX and FSZ. There's nothing in FX, but I just have them anyway. And normalize. There's my shear diagram, but I want to see the value. So I'm going to come up here. I'm going to click parameter, label, apply. And there it is. Okay, I'm going back to NIM. And I'm going to uncheck these because I want to know the moment now. So let's check the moment diagram. I'm going to click moment right here. Normalize. And there's my moment diagram. Now, if you have to do this on a paper, you'll be upside down. This is basically flip it over. And the reason is that because of the sign convention. Okay, so we're going to go ahead and do a couple of problems, do shear moment diagram. In this problem, we have a simply supported beam. That means indeterminate. And we have a pin and we have roller. And then at the 4 feet away from the beam, we have 20 kips. And the beam is 10 feet long. We like to know what the shear diagram and the moment diagram is. We can do this graphically first, but let's go first, before we go ahead, let's calculate the reaction forces. When we do a shear free body diagram, and this will be our load, 20 kips. So now we have the, I can write better 20. So we have these reaction force here, and these two reaction force here, and a load. And we talked about the three equation of equilibrium, which was summation fx is equal y, summation fy is equal 0, and summation moment about any point is equal 0. So let's go take a moment about B. Summation moment about point B is equal to 0. Our sign convention, let's say if we go counterclockwise, that's positive. So I got this load, and it's rotating clockwise, therefore it's negative. So I got minus AY times 10. And then I have nothing until I get to 20. And 20 rotate counterclockwise. So it's going to be plus 20 times the distance is going to be 6 feet here. So times 6 feet. And I have nothing else until I get here. And of course, these cannot take a moment about themselves because they're in the same spot. And moment is a perpendicular distance, which is nothing there, equals 0. And therefore, AY comes out to 12 kips. And we can do summation FOY. Direction going up is positive, equals 0. I have 12, that came out to 12. So 12 positive minus 20 and plus BY is equal to 0. So BY comes out to 8. And they both even out. So now let's go ahead and do moment shear diagram. Let's call this V for shear diagram. And when you look at it, the reaction here is 12. So I'm going to go up 12. That's 12 right there. And nothing happened until I get here. And it's 20. It's going to come down 20. I mean, right here be 8. And it comes back in here and it goes back up 8. And that's your shear diagram. That's a 12. This is a 8. And graphically, how we do that? Do the moment diagram. It's going to be linear. This is constant. That's going to be linear. It's going to be a step higher. And the area underneath here, it's going to be what's going to control here. So moment, when we have a roller, when we have a pin, there is no moment here. They cannot handle moment. So we know the moment start out at 0 at this location. But this is a positive as above, so it's going to go up right here. It's going to go like this linear. So what is the magnitude of that? It's going to be area underneath here. And the area, this is 12 times 4. We know that's a 4, so it's 12 times 4. So this magnitude is 12 times 4, which is equal 48. And that's a 48 right there. And you notice it's going to come down. It's going to come down and it's going to make it to 0 right at the reaction, right here. And this, it should be equal to that, which is 8 times 6. This is a 6 feet. Excuse me. So 8 times 6 is 48, and that's how your moment diagram is. Okay, we got second problem here. We got this beam. It's 4 meter long. The uniform distributed load is 3 kilonewton per meter. We're going to do a free body diagram. So we're going to have a roller here and pin there. Then we have one reaction here, two reaction there. And let's go ahead and calculate the reaction force first. And that's going to be, let's take a summation moment about point B is equal to 0. And then we're going to have, well, I'm going to convert this to a concentrated load, which becomes 12 kilonewton. Basically, it's the area underneath here, which is 3 kilonewton is the per meter, and then time the whole 4 meter become 12 kilonewton. So I'm going to say AY, it's going to be negative because it's rotating clockwise, minus AY times 4. Then I have this concentrated load, which is 12 times, that becomes 2 feet, 2 meters. And that's going to be positive. Plus 12 times 2 is equal to 0. Of course, that's the uniform distributed load. So therefore, AY comes out to 6 kilonewton, which is basically equal BY. Because if you do summation BY, comes out to the same. Summation FOY is equal to 0. Going up is positive. I have, this became 6. 6 minus 12 plus BY equals 0, and that's why BY became 6. Great. All right. So let's do the shear diagram. The shear diagram says this is going up 6. This is a 6 right here, and this is a 6. So it goes up 6 right here. Now be careful here. We have a uniform load. We just made it to a concentrated load to simplify so we can do this. So if I'm going up right here at 6 kilonewton, and it's coming down 3 kilonewton per meter. So by the time I get here, it's what? It'd be 3 times 2 is 6. So it's going to become, that'd be the center. It's going to come like that, and it's going to go up like that. And that's what it's going to be, 0 right down the middle. Assuming that's the middle. Now, we're going to do the, let's do the moment diagram. The moment diagram, this is a linear curve, so the moment is going to be parabolic, second degree curve. If this is the center right here, it's going to be something like that. Okay? The magnitude of this is the area of this triangle. The area of triangle is 1/2, 6, and we know this is 2 feet, and times 2 feet, therefore becomes 6. 6 kip foot. Okay, so this is the shear and moment diagram. What if? What if we want to know what's the moment right here, or right here? Want to know what the shear is right here, or right there? I mean, at any point along the length of the beam. That's where we're going to go ahead and calculate that. I'm going to take this beam right here. I'm going to cut it. This beam, I'm going to cut it. Right, this is my beam right here. I'm going to cut it out in some distance. I don't know. I'm going to call it X. anywhere from anywhere I want, call it x. And we know the loading on top of this is basically this is your loading right here. And that's a 3 kilonewton. We know that. And but the concentrator load for this load, it's going to be right here, the center, and it's going to be 3 kilonewton. Let's take the kilonewton out for now. It's going to be 3 times x, because we said the magnitude for this concentrator load, for this uniform distributed load, is the area underneath here, which is a 3 times width times length, and it's going to be 3 times x. So that's 3x. That comes out 3x. So when I cut this beam, there's something going to happen. I got to replace it, just like I have in a bridge beam. When we have the two bridge beam, because the girder are so long, and maybe 200 feet, and you cannot find a vehicle to carry 200-foot beam on a highway, so we have two 100-foot, and when you connect and make one beam out of them. And we do the same thing. What if I have a beam and if I connect it? For example, if I have this right here, what is the forces holding these together? If I cut it right here, what forces holding this together, making one unit? So I'm going to replace those forces with 3 forces that we talked about. Okay, let's talk about, we talked about a shear, a moment, and the actual force. We know there's nothing here because there's no force coming this way. So we have V and we have M. But I want to know what the magnitude of this. I know on this side, this force came out to be 6. So now I want to know, what is my shear at any point? What is my moment at any point of x? You know, this distance right here is x over 2. That distance is x over 2. All right, so I'm going to find out what shear is. We're going to use this equation, summation f of y is equal 0. Going up is positive. What do I have? I have 6 positive. Okay, I have nothing until I get here. I got minus 3x. Minus 3x. Then I come in here, I have nothing until minus v. Minus v, and that's it, is equal 0. Therefore, my v comes out to 6 minus 3x. So that's the equation. So if you ask me, oh, what is the shear at 2.5? All I gotta do, plug in 2.5. What is the shear as 2? It should be 0. Well, minus 3 times 2 is 6, and that becomes 0. That's the equation for this line. So I can tell you anywhere along the line what is my shear is. What about the moment? Let's do the moment. We have the same thing right here. We can take a moment about this point. Summation moment about this point. I don't know, call him MC. Call this point C right here. So this should be VC, but anyway, MC hammer, right? So going counterclockwise is positive. I'm going to take a moment about this point. I got this, right? 6 is going to go clockwise, so it's going to be minus. So it's going to be minus 6 times x. That's the distance. I have nothing until I get here. Then I have this times this x divided by 2. And this is 3x. So that's going to be plus. It's going to be plus 3x times x divided by 2. Then I have moment itself, and the moment, the way I have it, it's going counterclockwise, so it's positive. Plus m equals 0. And my m keep m and put it on the other side so they become positive 6x. And minus 3 times divided by 2 x squared. And there is the equation. So anywhere along this point, I can tell you what my moment is going to be. And that's how we're going to do a equation.